All right. Any questions? Any comments? Now I want to talk about something called rotational invariance, and I also introduce eigenfunctions of angular momentum. So first, let's think about rotational invariance. So here's our coordinate system. So for the moment, let me think about simple rotation around z-axis. So this is x and y, and after the rotation, I don't know, something like this. I have some rotation by some angle theta. Let's call this x prime and y prime, and amount of rotation is theta. Okay? And after the rotation, my x, y, and z goes to x prime, y prime, and z prime. Because rotation is around z prime, it's equal to z. There's no change. Whereas x prime, right, I think this is standard. Let me just write the result. Cosine theta x minus sine theta y, and y prime is equal to sine theta x plus cosine theta y. Actually, let me write them in sorted manner. And you can also obtain inverse immediately. So inverse is going to be x here, x prime, y prime here, and theta will go to minus theta in the inverse, right? From the x prime point of view, x rotated but in the opposite direction. So theta goes to minus theta. This one is going to be plus. This one is going to be minus. This one is going to be plus. So this is inverse transform. And this is x, y, z, prime, 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 prime. Good. So under this effect, we can immediately calculate, let me call it r prime squared is equal to x prime squared plus y prime plus z prime squared. And right, it's like, so the square of this, we can think about this to be like a unit vectors if you want, right? And then in that case, x squared is going to be cosine squared plus sine squared is x squared, right? Or here, cosine squared plus sine squared is 1. Sine squared plus cosine squared is also 1. And z is also z squared. That means r prime goes to r. There is no change in the r. And that's what we know, right? The magnitude of vector does not change with rotations. And the second thing to consider is like change of this x prime squared plus del y prime squared plus del z prime squared. And this is going to be equal to, I can use this one, right? This is going to be, let me write it here, not to make a mistake here. So this is del x prime, del x plus del x, del y, del x prime, del y, and there's no z. So del x prime is cosine theta. So this is cosine theta del, so this is equal to del x. And this second one, y derivative with respect to prime. So this is del y del x prime, del y del x minus sine theta. del y. And similarly, this one is, let me just write the result. So this is sine theta del x plus cosine theta del y. And when you take the square, you can see cosine square plus sine square is 1. So this is going to be del squared del x squared plus, or I can write it in the same form. So this is squared plus del y squared. Right? This is sine squared plus cosine squared is 1 plus z. There is no change in z anyways. Del z squared. And from here, this Laplacian is also invariant, right? So Laplacian is invariant, R is invariant. Therefore, if we have like a Hamiltonian where like something like p squared over 2m plus v of r, so this is like central potential. That means h in the new coordinate, h prime is equal to h. So Hamiltonian is also rotationally invariant. Good. Of course, this is invariant for central potential. There may be other system that this rotational invariance is broken. Any questions? Now let's consider what follows is valid for any rotation, but sometimes in the calculations it's easier to consider infinitesimal rotation. So infinitesimal rotations, and sine theta in that case is approximately theta, and cosine theta is approximately 1, and the transformation above becomes x prime is equal to x minus theta y, and y prime is equal to y plus theta x, and z prime is equal to z. Good. And now I want to consider h, I don't know, x, y, z, psi x, y, z is equal to e psi x, y, z. And I want to see how this equation transforms in the prime coordinates, like this. And I want to write this, okay. So this is given without prime. So this is given. Right, now I want to put this prime, but from, okay, to reduce the clutter, let's erase this. I know h is invariant anyways, right? H prime is equal to h, so let's erase this part, and let's also erase this. This is the invariant part. And now I want to look at this expression. So this psi x prime, y prime, z prime is equal to, we just have psi x minus theta y, y plus theta x, and z prime is equal to z. And I'll do the Taylor expansion. So the lowest order is psi x, y, z plus first order here is like minus theta y del over del x psi. Also, to avoid clutter, let me say whenever there is no argument, it is x, y, z, right? So let's do it like this. And the same thing here, plus theta x del over del y psi, and higher order. But for infinitesimal rotation, higher orders can be neglected. And this thing, I want to use LZ to write this thing. LZ is equal to x py minus y px. And this is equal to minus I h bar. So So this is x del over del y, and I take this minus y del over del x, and from here I see, okay, so this is equal to psi minus theta y del, actually let me write it like this, plus x del y minus y del x acting on psi. And from here I see this operator, so this thing from the angular momentum definition. So this piece is I over h bar times Lz, right? Now I want to go back to Schrödinger equation and put this there. So this is h, lowest order term is psi plus I over h bar theta Lz psi is equal to, on the other side I have E times the same thing, E times psi plus I over h bar theta Lz psi. Good? But h psi is given to be E psi, then I can cancel, let me write it in two steps, h psi plus I over h bar theta h Lz psi is equal to E psi plus I over h bar theta E Lz psi. H psi is E psi given to us in the original coordinate. So this is the given. Cancel that with that. And the remaining condition is, right, the lowest order term is H Lz psi is equal to E Lz psi. Good. Now I want to, so this is just a number. I can just commute through Lz. So this is Lz times E psi. And E psi from the original equation is equal to Lz H psi. Now I can combine this and this on the same sides. And what I find is H Lz minus Lz H acting on any function psi is 0. Then if there is rotational invariance, we have H Lz commutation 0. Okay? And another way to say there's rotational invariance is to say that's the commutation relation. If there's this symmetry, yes. So I took the lowest terms are like lowest order is H psi is E psi. This is one equation. And the next is everything is multiplying I, right? Good. Thank you. But there is nothing special about Lz, right? If this happens with Lz, right? X, Y, and Z are the labels I put. You could just put them in the other order. That means immediately H Lx is also 0. And H Ly is also 0. So this is the full statement about rotational invariance. So Lx, Ly, and Lz commute with Hamiltonian, but they don't commute with each other, right? That's important detail. So, but Lx, Ly not equal to 0. So that's not a necessary condition. So if H commutes with Lx, Y, and Z, that means H also commutes with Lx squared. Right? If something commutes with some operator, it also commutes with square of this operator. That's trivial. If anybody has doubts, I can show. Then also Ly squared, also Lz squared, or I can combine all of them and I say H also commutes with L squared. Okay, so H commutes with L squared, H commutes with Lz, and L squared commutes with and L squared commutes with Lz. Therefore, H, L squared, and Lz are a commuting set. Operators. Then I can use their eigenfunctions because they have common eigenfunctions. Right? They can be diagonalized simultaneously. And this is why we have label n for n, label L for L squared, and label m for Lz, and our wave functions are labeled with n, L, m. Okay, that was like a theorem we proved a while ago without appealing to any concrete system. Now let me talk about eigenfunctions. And so this is our coordinate system. Let's say this is my R. So this is perpendicular. So this is X, Y, Z. So this angle is theta, and this angle is phi. And angular momentum L is equal to minus I h bar R cross nabla. In these coordinates, R is simple. This is R times R hat. And I need to write everything in terms of R hat, theta hat, and phi hat. Or you can use it from the mathematics books. The result is something like that. Nabla is equal to R hat del R plus theta hat 1 over R del theta plus phi hat 1 over R sine theta del phi. Then L is equal to minus I h bar. So let me open up this space. So R cross R is going to be 0. So let's write only the non-zero terms. It's like this. And I need to have R cross this and R cross this. There's also additional R, which is going to cancel this and this. Right? So this is like a parenthesis. And R, theta, and phi are like orthogonal coordinates. R theta is going to give us phi hat, and R phi is going to give us minus theta hat. Minus theta hat. Okay, this is a little bit. Minus I h bar phi hat del theta. Okay, not too bad. You can also do the inverse, right? You can go from theta r theta phi to x, y, z coordinates. And let me just write, for example, for theta hat, you can write it in terms of cosine theta, cosine phi, I hat, plus cosine theta sine phi j hat minus sine theta k hat, and similarly phi hat is going to be minus sine phi I hat plus cosine phi j hat. And you can substitute this there, and for example, you can read each one, right? The most important one is LZ, because LZ is special. Let me just write that. This is like minus I h bar del phi. By just reading the J, you can just get this out. And the others are like Lx minus I h bar minus sine phi del theta minus cosine phi cotangent theta del phi, and the other one is very similar to this one. So this is Lx, and this one is plus cosine theta. So this is cosine theta, and this one is minus. It's exactly the same. Good. What's that? Oh yes, thank you. So you can also, right, these are what we started with. We can also calculate L plus and L minus. All right, you can, this is like L, this plus I times this, and they are something like this. Let me just write the expression: plus or minus h bar e to d plus or minus I phi del theta plus or minus I cotangent theta del phi. And so you can calculate things like this. For example, L plus times L minus. And now I think everybody knows you have to be careful when you do these things, right? Because there is like a derivative inside this thing, and that derivative can act on here, or that derivative can act on something after here. Right? That's like important detail. But other than that, that's like a mundane calculation. You just do partial derivatives, and the result is something like that: minus h bar squared del theta plus cotangent theta del theta plus cotangent squared theta del squared del phi squared plus I del phi. So this is your exercise. So if you want to know if you understand the commutations, try to show this. It's not very pleasant, but it can be done. Also, this L squared is more important. So this is minus h bar squared 1 over sine theta del theta sine theta del theta plus 1 over sine squared theta del squared del phi squared. So this is also exercise, right? You need to do a lot of things, right? I think nobody would enjoy if I did this here and then you had to sit for like 10 minutes exercise. But once you do that, right, the nice thing about this is like, so this L squared times F Lm is exactly the spherical harmonics we introduced when we were doing the separation of variables in spherical coordinates. And from there, the eigenvalues are these spherical harmonics, and they are h bar squared L plus 1 F Lm. I think we wrote expressions for this, and Lz times Fl. So this is also trivial. It's going to be h bar m Flm. Now the complete picture is like H psi is equal to E psi, right? And L squared psi is equal to this eigenvalue times psi, and Lz psi is equal to this eigenvalue. And Hamiltonian can also be written in terms of this. It's rather nice. It's like 1 over 2m r squared minus h bar squared del r del r plus L squared. So this L as an operator is this differential operator. And we now know the solution of this whole set. Good? Any questions? If not, maybe I can stop here and start talking about spin next time. Thank you.